You think you know what the universe is. After all, you've lived your entire life inside it. You wake up. The sun rises. Time moves forward. Objects stay where you place them. Cause comes before effect. The past feels fixed, the future open. These ideas feel so natural, so deeply woven into everyday life, that questioning them almost feels unnecessary. And yet, modern physics quietly suggests something very different. According to our best theories, tested again and again with extraordinary precision, the universe is far stranger than common sense allows. Time doesn't behave the way it feels. Space isn't the empty stage it appears to be. Matter, energy, and even existence itself don't follow the rules our intuition expects. The universe described by physics barely resembles the universe we experience. Not because our experiences are wrong, but because they are limited. Often these ideas are softened, simplified, made comfortable. Not because they aren't true, but because they're difficult to sit with. Tonight, we won't rush. We won't dramatize. We'll gently explore some of the most surprising facts modern science has revealed, ideas that emerge naturally from relativity, quantum mechanics, cosmology, and thermodynamics. Not to overwhelm the mind, but to let it wander. I'm the sleepless astronaut, and tonight, as your body rests, we'll let your thoughts drift through a universe that's quieter, deeper, and more mysterious than it first appears. Let me give you a taste of what's coming. Right now, as you watch this video, time is passing at different rates for different parts of your body. Your head is aging faster than your feet, not by much, but measurably, provably faster. The atoms in your left hand were forged in a different star than the atoms in your right hand, possibly billions of years apart, certainly light years apart in space. Every particle in your body has existed for nearly 14 billion years, cycling through stars and planets and cosmic dust before temporarily organizing into the pattern you call you. The sun you see in the sky? That's where the sun was 8 minutes ago. It could have exploded 7 minutes ago, and you'd have no way of knowing. You'd sit here, comfortable and ignorant, for one more minute before the last photons reached you and everything you've ever known vanished in an expanding sphere of plasma. Every star you see at night is even worse. You're looking at ghosts, light from objects that might have died before humans even existed. And that's just the beginning. That's the comfortable stuff. Time the thing you've experienced every moment of your existence. The relentless forward march from past to future doesn't actually exist the way you think it does. According to relativity, there is no universal now. The present moment is different for every observer. Your past and future are equally real, already existing, frozen in place in something called the block universe. Free might be an illusion. Your death has already happened from certain perspectives. The universe is deterministic, and you're just watching a movie that's already been filmed. Black holes aren't just super-dense objects that suck things in. They're tears in space-time where the mathematics of reality breaks down, where time stops and space becomes time, and nothing makes sense anymore. Fall into one, and you'll be stretched into a strand of atoms spaghettified, while simultaneously, from an outside observer's perspective, you freeze at the event horizon forever, a two-dimensional hologram smeared across the surface. Both descriptions are true. Reality contradicts itself at black holes, and we don't know why. Quantum mechanics is worse. The double-slit experiment, a basic physics demonstration you can do in a high school lab, suggests that reality literally doesn't exist until it's observed. Particles don't have definite positions or velocities until you measure them. They exist in ghostly superpositions smeared across space until consciousness collapses them into actuality. Some interpretations suggest the universe requires observers to exist. Take away consciousness, and maybe nothing is real. Think about that. The universe might need you. Not humanity, you specifically, this particular arrangement of atoms watching this video. Without observation, quantum systems remain in superposition. Without consciousness, maybe the entire universe is just a probability wave, a mathematical fiction that never actualizes into reality. And it gets stranger. You're probably living in a computer simulation, not metaphorically, literally. The simulation hypothesis isn't science fiction anymore. It's a serious philosophical argument that some physicists take very seriously. The math suggests that if it's possible to create realistic simulations of universes, then statistically, we're almost certainly in one. The base reality civilization could run trillions of simulations, meaning the odds that we're in the original, unsimulated universe are essentially zero. There's evidence, too. Quantum mechanics acts suspiciously like a computer program, rendering only what's being observed to save processing power. The speed of light acts like a frame rate limit. Planck length acts like pixel size. These aren't proofs, but they're unsettling coincidences. The universe is also trying to kill you, not metaphorically, literally. Right now, this moment, a bubble of true vacuum could be expanding toward you at the speed of light, a quantum phenomenon that would erase you, Earth, the solar system, and everything in the observable universe without warning. You never see it coming. Light from the destruction wouldn't reach you before the destruction itself. One moment you exist. The next moment you don't, with no transition between. This isn't speculation. This is called vacuum metastability, and our universe might be in a false vacuum state, a temporary, unstable configuration that could decay into true vacuum at any moment. It might have already happened somewhere distant, and the expanding sphere of annihilation is racing toward us right now. We wouldn't know until it arrived. And even if we avoid that, the universe has an expiration date. Heat death is inevitable, the point when entropy maximizes. All useful energy is gone, and nothing can ever happen again. The universe will become a cold, dark, featureless void where even atoms decay and black holes evaporate, and literally nothing exists except random quantum fluctuations in an infinite sea of nothing. This is guaranteed. It's not a theory. It's thermodynamics. We're going to explore all of this. 10 reality-breaking facts that physics has discovered, each one stranger than the last, each one supported by evidence and mathematics. We'll talk about why time might not exist, why you're made of dead stars, why black holes break physics, why consciousness might be fundamental to reality, why everything you see is a lie, why the universe will definitely kill you, why you're probably simulated, why your future already happened, why anything exists at all, and why the universe might have been created 5 minutes ago with all your memories pre-installed. These aren't clickbait exaggerations. These are real consequences of real theories taken seriously by real physicists. I'm not going to water them down or make them comfortable. I'm going to tell you what the universe actually is, according to our best current understanding. And I guarantee you've never heard most of this before. Not because it's too complicated, it's not, but because it's too disturbing. Because once you understand these things, you can't go back to seeing reality the way you used to. Some of you will finish this video and wish you hadn't watched it. That's fine. Ignorance is comfortable. But some of you, the curious ones, the ones who want to know what's really true, even if it's terrifying, you're going to love this. So buckle up. Turn off your intuition. Prepare to have everything you believe about reality systematically dismantled. Let's talk about what the universe actually is. Let's start with something you experience every single moment of your existence. Time. The relentless march from past to future. The steady tick of clocks, the aging of your body, the progression of cause and effect. Time seems like the most fundamental aspect of reality, the stage on which everything else happens. Here's the problem. According to physics, time as you experience it doesn't exist. At all. I don't mean this philosophically or poetically. I mean the equations of physics, the ones that describe reality with stunning accuracy, the ones we use to build GPS satellites and particle accelerators. Those equations treat time completely differently than you experience it. And when we take those equations seriously, when we follow them to their logical conclusions, time as a flowing river from past to future simply vanishes. Let me show you what I mean. Right now, time is passing at different rates for different parts of your body. This isn't metaphor, it's measurable reality. Your head is aging faster than your feet. Not by much, we're talking nanoseconds over a lifetime, but the effect is real and has been confirmed by atomic clocks. Place one atomic clock on the floor and another on a table, and the one on the table will tick faster. Time literally moves faster the farther you are from Earth's center. This is called gravitational time dilation, a consequence of Einstein's general relativity. The stronger the gravitational field, the slower time passes. And this isn't some tiny correction we can ignore. GPS satellites have to account for it constantly. Those satellites orbit about 20,000 kilometers above Earth's surface, where gravitational time dilation causes their clocks to run faster than clocks on the ground, about 45 microseconds per day faster. But wait, there's another effect. Those satellites are also moving at about 14,000 kilometers per hour relative to Earth's surface. And according to special relativity, moving clocks run slower than stationary ones. This is called velocity time dilation, and it causes the satellite clocks to run about 7 microseconds per day slower than ground clocks. Put both effects together. Gravitational time dilation speeds the clocks up by 45 microseconds per day. Velocity time dilation slows them down by 7 microseconds per day, for a net effect of 38 microseconds per day faster. This doesn't sound like much, but GPS requires nanosecond precision. Without correcting for relativistic time dilation, GPS would accumulate errors of about 10 kilometers per day. Your navigation would be useless within hours. Think about what this means. Time isn't universal. There's no cosmic clock ticking away at the same rate for everyone. Every object, every observer has their own personal time, running at whatever rate the local gravitational field and their velocity dictate. Your time is different from my time. The Earth's time is different from the Sun's time. Nothing is synchronized. But it gets worse, much worse. Imagine you're standing next to a black hole, not falling in, just hovering near the event horizon using a rocket engine. Time for you in that intense gravitational field would slow down dramatically compared to someone far away. If you spent 1 hour near the event horizon and then returned to Earth, decades might have passed here. Your friends would be old or dead. The world you left would be gone. This is the plot of the movie Interstellar, and it's completely accurate physics. On the water planet orbiting Gargantua, the black hole in the film time moves so slowly that 1 hour there equals 7 years on Earth. The crew spends a few hours on the surface, and when they return to their ship, 23 years have passed. Their colleague has aged 2 decades while they aged hours. This isn't fiction. This is what general relativity predicts. And general relativity has passed every experimental test we've thrown at it. Get close enough to a black hole, and time dilation becomes extreme. At the event horizon itself, the point of no return time stops completely. From the perspective of someone far away, an object falling into a black hole never actually crosses the event horizon. It gets slower and slower, redshifts toward infinity, and freezes. Forever. You'd see it stuck there, a two-dimensional image smeared across the surface, never falling in, preserved for eternity. But from the perspective of the person falling in, they cross the event horizon in finite time. Nothing seems unusual, no barrier, no indication that they've passed the point of no return. They just keep falling. Both perspectives are correct. Reality contradicts itself. Time stops and doesn't stop, simultaneously, depending on who's watching. This isn't a problem with our understanding. This is what the universe actually does. Time is observer-dependent. Now let's talk about the twin paradox. And this is where things get really disturbing. Imagine twins, Alice and Bob. Alice stays on Earth. Bob gets on a spacecraft and accelerates to 99.5%. The speed of light travels for what feels to him like 5 years to a distant star, turns around and comes back. When Bob returns, he's aged 10 years. Alice is aged 70 years. Bob is still young. Alice is elderly or dead. This isn't hypothetical. This is real physics, confirmed by experiments with particles and atomic clocks on airplanes. Travel fast enough and time literally slows down for you, relative to stationary observers. But here's the disturbing part. From Bob's perspective during the journey, it's Alice who's moving. Special relativity says motion is relative. You can't tell who's really moving. So shouldn't Alice be the one aging slowly? The resolution is that Bob accelerates, turning around to come home, breaking the symmetry. But that's not the disturbing part. The disturbing part is what happens to now. When Bob is traveling away from Earth at 99.5% light speed, the question, what is Alice doing right now, has no answer. Or rather, it has multiple answers depending on Bob's reference frame. If Bob is moving away from Earth, now for Alice might be 10 years in Earth's past. If Bob turns around and heads home, now for Alice suddenly jumps 40 years into Earth's future. Just by changing velocity, Bob changes which moment in Alice's timeline is simultaneous with his. Now isn't a fixed thing. The present moment, the universal now that you think separates past from future, doesn't exist. Different observers have different nows, and they're all equally valid. This is called relativity of simultaneity, and it destroys the common sense notion of time. There is no universal present. The universe doesn't have a now. Events that are simultaneous for you might be separated by years for someone moving relative to you. Think about what this means. Right now, as you watch this video, there are events happening on distant planets that are for you simultaneous with this moment. But for an alien traveling at high speed relative to Earth, those same events might be in Earth's deep past or distant future. Nothing is actually happening now in any absolute sense. Now is just an artifact of your reference frame, and this leads to something even more disturbing: the block universe. If there's no universal now, if different observers disagree about which events are simultaneous, then in what sense is the present special? Why should now be more real than yesterday or tomorrow? The answer, according to many physicists, is that it isn't. The past, present, and future are equally real. They all exist simultaneously in a four-dimensional structure called the block universe. You're not moving through time. You're a four-dimensional object, a world line extending from your birth to your death. All moments of your life exist at once, frozen in the structure of space-time. You experience time flowing because your consciousness traces along your world line, from past moments to future moments. But the future is already there, already determined, already real. It exists right now in exactly the same way that yesterday exists. The feeling of time flowing, of the present being special, is an illusion created by how your consciousness processes memory. From this perspective, your entire life, every moment from birth to death, already exists, has always existed, will always exist. You're not traveling through time. You're a static object in four-dimensional space-time, unchanging and eternal. What you call now is just one slice through that four-dimensional structure, no more special than any other slice. This is profoundly disturbing. If the future already exists, then it's determined. Your choices are already made. Free will is an illusion. The block universe is deterministic. Every event that will ever happen has already happened from a timeless perspective. You might object. Quantum mechanics introduces randomness, preserving free will. But even that doesn't help. Quantum randomness isn't choice, it's dice rolls. If your actions are determined by random quantum fluctuations, that's not free will either. That's just determinism with noise. And the block universe resolves all those time dilation paradoxes. There is no universal now, because all moments exist simultaneously. Time doesn't flow. It's just another dimension, like space. The past isn't gone. The future hasn't happened yet. Both of those statements are wrong. Everything exists timelessly in the four-dimensional structure of the universe. Some physicists go further. They argue that time is an emergent property, something that appears only at macroscopic scales, but doesn't exist at the fundamental level. The equations of physics, particularly quantum gravity theories, often work better without time as a variable. Time might be like temperature, a useful statistical concept that emerges from large numbers of particles, but not a fundamental feature of reality. So when we say time doesn't exist, we mean it literally. The flowing, directional time you experience, past leading to present leading to future, is an illusion created by your brain, a useful fiction that helps you navigate reality, but doesn't correspond to anything fundamental in the universe. The universe is timeless. All moments exist eternally, and you reading this are just one slice through a four-dimensional structure that contains every version of you that has ever existed or will ever exist, frozen forever in the unchanging geometry of space-time. Your past is still happening. Your future has already happened. And the present? The present doesn't exist at all. Welcome to relativity. You've probably heard the phrase, "We are made of stardust." It's poetic, romantic, the kind of thing Carl Sagan would say while gazing wistfully at the cosmos. It sounds like metaphor, like something meant to make you feel connected to the universe in some vague, spiritual way. Except it's not metaphor, it's not poetry. It's literal, specific, traceable fact. And when you understand the details, when you follow the actual path that the atoms in your body took to get here, it's far more incredible than the simplified version suggests. Every atom in your body except hydrogen was forged inside a star, not figuratively, not inspired by stars or similar to stellar material, actually physically created in the core of a massive star through nuclear fusion billions of years before you were born. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it was manufactured in stellar furnaces and scattered through space when those stars died. But it's more specific than that. Different atoms came from different stars, different types of stars, different stellar processes. Your body is an archaeological record of stellar evolution, a museum of cosmic history. Let me show you exactly where you came from. Start with hydrogen. The hydrogen in your body, about 10% of your atoms, wasn't made in stars. It's primordial, created in the first 3 minutes after the Big Bang, roughly 380,000 years after the universe began. Space was filled with a hot plasma of protons, electrons, and photons. As the universe expanded and cooled, protons captured electrons, forming neutral hydrogen atoms. This is called recombination, and it's when the universe became transparent photons could finally travel freely, and the cosmic microwave background radiation was born. So the hydrogen in your body is 13.8 billion years old, older than stars, older than galaxies, primordial matter from the Big Bang itself. When you drink water, you're consuming atoms that have existed since the first moments of the universe. But hydrogen is simple, just a proton and an electron. Everything else had to be built. The helium in your body, not much of it, but some was also mostly created in the Big Bang. During those first 3 minutes, when temperatures were high enough for nuclear fusion, protons and neutrons combined to form helium nuclei. About 25% of the universe's normal matter is helium, nearly all of it primordial. The helium you occasionally inhale to make your voice squeaky is Big Bang material. But the Big Bang only created hydrogen and helium with trace amounts of lithium. That's it, 3 elements. Everything else, carbon, oxygen, nitrogen, calcium, iron, all the elements that make complex chemistry possible, that make life possible, had to be built later in stars. This is stellar nucleosynthesis, and it's the most important chemical process in the universe. Here's how it works. Stars form when clouds of hydrogen and helium collapse under their own gravity. As the cloud contracts, it heats up. Eventually, the core becomes so hot and dense that hydrogen nuclei overcome their electromagnetic repulsion and fuse, creating helium and releasing energy. This is how stars shine by, converting hydrogen into helium through fusion. But fusion doesn't stop there. When a star exhausts its core hydrogen, it starts fusing helium into carbon and oxygen. This requires higher temperatures, around 100 million degrees, but massive stars achieve it easily. Carbon forms when three helium nuclei fuse simultaneously in a process called the triple alpha process. And this is where you begin. The carbon in your body, the foundation of organic chemistry, the element that makes life possible, was created by three helium nuclei colliding in the core of a red giant star, probably 5 or 6 billion years ago. That star wasn't the sun. The sun isn't massive enough to create significant carbon. The carbon in your body came from a larger star, somewhere else in the galaxy, that lived and died before the solar system formed. Those carbon atoms drifted through space as part of a molecular cloud, eventually getting incorporated into the disk of gas and dust that formed the sun and planets. Some of that carbon ended up on Earth. Some of it ended up in your body. Oxygen is similar. When helium burns in a star's core, it creates carbon and oxygen. The oxygen you breathe, the oxygen in water, the oxygen bonded to carbon in every organic molecule, all of it was forged in the cores of massive stars and expelled into space when those stars died. About 65% of your body mass is oxygen, 18% is carbon. Together, they make up over 80% of your mass, and all of it came from stars that died before the sun was born. Nitrogen is trickier. It's created through the CNO cycle, a fusion process that uses carbon, nitrogen, and oxygen as catalysts to convert hydrogen into helium. Nitrogen is continuously created and destroyed in this cycle, and significant amounts are produced in the final stages of massive stars. The nitrogen in your DNA, in your proteins, and every amino acid stellar product, created in stars and scattered into space. But the really interesting elements are the heavy ones. Iron, for instance. Iron is the most stable nucleus. Fusing elements lighter than iron releases energy. Fusing elements heavier than iron requires energy. This means stars can build up to iron through normal fusion, but they can't go further. It would consume more energy than it produces. So where does the iron in your blood come from? Supernova. When a massive star, at least 8 times the sun's mass, exhausts its nuclear fuel, fusion stops. The core, no longer supported by the outward pressure of fusion, collapses catastrophically. In less than a second, the core implodes, reaching densities comparable to atomic nuclei. Electrons are crushed into protons, forming neutrons. The collapse halts when the core becomes a neutron star, and the infalling material rebounds, creating a shock wave that tears through the star's outer layers. This is a core collapse supernova, and it's the most violent event in the universe, short of a gamma-ray burst. For a few weeks, the exploding star shines with the luminosity of an entire galaxy, billions of stars worth of light, all from one dying sun. And in that explosion, in the intense heat and pressure, elements heavier than iron are forged. Gold, silver, platinum, uranium, all the heavy elements exist because of supernova. They can't be created any other way. The gold in jewelry, the uranium and nuclear reactors, the tungsten in light bulbs, all supernova products, created in seconds during stellar death. The iron in your blood specifically came from a supernova, not the same supernova that created the gold on Earth. Many different supernova contributed to the solar system's material, but definitely a supernova. Every iron atom in your body was created in the collapsing core of a dying star, moments before that star exploded with the force of 10 billion trillion trillion megatons of TNT. You are quite literally made of stellar corpses. But wait, there's more. Because not all heavy elements come from supernova. Some come from neutron star collisions. When two neutron stars orbit each other, they emit gravitational waves, ripples in space-time that carry energy away from the system. Over millions or billions of years, the orbit decays, and eventually the neutron stars collide, merging into either a more massive neutron star or a black hole. These collisions are even more violent than supernova. For a brief moment, they create conditions so extreme that elements heavier than iron are produced in vast quantities through rapid neutron capture, the R process. Gold, platinum, and rare earth elements are mostly created this way, not in supernova. In 2017, we detected gravitational waves from a neutron star merger, and telescopes observed the aftermath, a kilonova, an explosion that synthesized about 10 Earth masses worth of gold and platinum. The gold in your ring, the platinum in catalytic converters, possibly even some of the iron in your blood. It came from events like this, from the collision of dead stars, from cosmic cataclysms so violent that space-time itself shudders. So let's inventory your body's cosmic origins. The hydrogen 10% of your atoms is primordial from the Big Bang 13.8 billion years old. The oxygen and carbon, over 80% of your mass, came from massive stars that lived and died before the solar system formed 5 to 10 billion years ago. These atoms were created in the cores of red giants and dispersed into space when those stars expelled their outer layers or exploded as supernova. The nitrogen 3% of your mass came from similar stars produced through the CNO cycle and released during stellar death. The calcium in your bones came from supernova, created in the violent explosion of massive stars. The iron in your blood enough to make a small nail came from either supernova or neutron star collisions, forged in some of the most energetic events in the universe. Trace elements, zinc, copper, iodine, dozens of others, came from various processes: supernova, neutron star mergers, cosmic ray spallation. Your body is a mosaic of stellar products, atoms forged in different stars at different times, in different parts of the galaxy, all eventually coming together in the molecular cloud that formed the solar system 4.6 billion years ago. And here's the really mind-blowing part. The atoms in your left hand probably came from different stars than the atoms in your right hand. The solar system formed from a molecular cloud, a vast, diffuse collection of gas and dust spanning light years. That cloud was itself made of material from hundreds or thousands of different dead stars all mixed together. When the cloud collapsed to form the sun and planets, nearby atoms might have had very different histories. The carbon atom in one of your DNA bases might have come from a red giant that died 8 billion years ago, 500 light years from where the sun would eventually form. The carbon atom right next to it in the same molecule might have come from a different red giant that died 6 billion years ago, 300 light years away in a different direction. You are not just made of stars, you are made of many stars, a patchwork of stellar products assembled by chance into the temporary pattern you call you. And those atoms were old even when Earth formed. The carbon in your body is 5 to 8 billion years old. The iron is 5 to 10 billion years old. These atoms existed for billions of years before Earth, cycling through the galaxy, drifting in molecular clouds, perhaps passing through other stellar systems, possibly even being part of other planets before ending up here. The atoms in your body have been recycled countless times. They were once in other people statistically. You contain atoms that were once part of Julius Caesar, Cleopatra, Shakespeare, every person who ever lived. You contain atoms that were once in dinosaurs, in the first bacteria, in ancient oceans, in the earliest rocks. But before all that, before Earth, before life, before the solar system, your atoms were inside stars, not orbiting them, inside them, in the cores where temperatures reach millions of degrees, where nuclear fusion creates the elements. You are not metaphorically stardust. You are literally stellar material. Every breath you take contains atoms forged in dying stars. Every heartbeat pumps blood filled with supernova products. Every thought you think happens in a brain made of matter created in cosmic furnaces billions of years ago. Carl Sagan was right. We are made of star stuff. But the reality is even more poetic than he knew. We're not just made of stars, we're made of specific stars from specific explosions, from specific moments in cosmic history. We're made of the universe's violent past, its creative destruction, its cycle of birth and death and rebirth. And in a few billion years, when the sun becomes a red giant and incinerates Earth, the atoms in your body will be scattered back into space. They'll drift in the interstellar medium, eventually becoming part of new molecular clouds. Those clouds will collapse, forming new stars and planets. And the carbon that's currently in your body might end up in some alien organism on a planet that doesn't exist yet, orbiting a star that hasn't formed yet, having adventures you can't imagine. You are a temporary arrangement of stardust, a brief pattern in the eternal cycle of cosmic recycling. And that's not depressing, it's magnificent. You are the universe experiencing itself, made of matter forged in stellar furnaces, assembled by gravity and chemistry into a form capable of looking back at the stars and recognizing your origin. Welcome home. And now, one more fascinating thing. Black holes are stranger than you think. Black holes are the universe's ultimate nightmare. Dense enough to trap light, powerful enough to tear stars apart, mysterious enough that we still don't fully understand what happens inside them. You've probably heard the basics. Massive stars collapse, creating objects so dense that nothing can escape their gravity. Space and time break down. They're terrifying, but the reality is so much worse than that. Black holes aren't just extremely dense objects with strong gravity. They're places where the rules of physics stop working, where space and time trade places, where reality contradicts itself in ways that should be impossible. They're not just strange, they're proof that the universe is fundamentally broken, that our theories hit a wall and shatter. Let me show you just how nightmarish black holes actually are. Start with spaghettification. This is the playful name physicists gave to being torn apart by tidal forces. And it's not an exaggeration. You literally get stretched into a long, thin strand of atoms. Here's how it works. Gravity gets stronger as you get closer to a massive object. Near a black hole, this gradient becomes extreme. If you're falling feet first toward a black hole, your feet are closer to the singularity than your head. They experience stronger gravity, much stronger. The difference in gravitational force between your head and feet creates a tidal force that stretches you. Near a stellar mass black hole 1 formed from a collapsed star, maybe 10 times the sun's mass. These tidal forces become lethal well before you reach the event horizon. Let's do the math. The tidal acceleration, the difference in gravitational pull between 2 points separated by distance depends on the black hole's mass and your distance from it. For a 10 solar mass black hole, tidal forces become unsurvivable at about 500 kilometers from the event horizon. Your body can tolerate maybe a few G's of acceleration difference between head and feet before structural damage occurs. Near a black hole, you'll experience thousands of G's. Your feet accelerate toward the singularity faster than your head can follow. The atomic bonds holding your body together aren't strong enough to resist. You stretch. First your legs elongate, bones pulling apart, tendons snapping. Then your torso, ribs separating, spine extending. Your skin tears. Your blood vessels rupture. But it doesn't stop. The stretching continues, accelerates. Your body becomes longer and thinner, a grotesque caricature of human form. Organs liquefy under the stress. Bones fragment. Eventually, you're not recognizable as a body anymore. You're just a stream of organic matter, cells, and molecules in a thin line. And still it continues. Molecular bonds break. Molecules stretch. Individual atoms are pulled apart. Electrons torn from nuclei. You become a strand of subatomic particles, falling in a single file line toward the singularity. This is spaghettification, and the worst part? You're probably conscious for the beginning. The brain is resilient. You might experience the initial stretching, the sensation of your legs being pulled away from your body, the awareness that something is catastrophically wrong before shock or oxygen deprivation kills you. But here's something even stranger. The size of the black hole matters. For a stellar mass black hole, spaghettification happens well before you cross the event horizon. You die in observable space, visible to outside observers. But for a supermassive black hole like the ones at galactic centers, millions or billions of solar masses, the event horizon is enormous, and tidal forces at the horizon are weak. Sagittarius A*, the supermassive black hole at the Milky Way's center, has an event horizon about 12 million kilometers in radius. At that distance from the singularity, tidal forces are negligible. You could cross the event horizon alive, intact, unaware that anything changed. You'd fall through the point of no return, and nothing would seem different. No wall, no barrier, no indication you just crossed into the region where escape is impossible. You'd keep falling deeper into the black hole, tidal forces gradually increasing, until eventually minutes or hours later spaghettification would begin. By then, you're already doomed. You crossed the event horizon minutes ago. No signal can escape to warn others. From the outside universe's perspective, you're already gone. But wait, I said you're already gone from the outside perspective. That's because of time dilation. And this is where things get truly bizarre. Remember relativity. Time slows down in strong gravitational fields. Near a black hole, this effect becomes extreme. As you fall toward the event horizon, time for you continues normally, but time for the rest of the universe speeds up. You look up away from the black hole, and you see the universe aging and fast forward. Stars born, live, die. Galaxies evolve. Billions of years pass in moments. And from the outside perspective, you slow down. As you approach the event horizon, you move slower and slower from an external observer's viewpoint. Your clock ticks slower. Your movements become sluggish. Light from your redshift stretched to longer and longer wavelengths. At the event horizon, from an outside perspective, you stop. completely. Time dilation becomes infinite. You freeze, a two-dimensional image smeared across the event horizon surface forever. Light from you continues escaping, red-shifted to radio waves, then to wavelengths so long they become unmeasurable. But the information about your last moment, the instant you reach the horizon, remains permanently visible. You never cross the event horizon from an outside perspective. Never. You just get asymptotically closer, frozen in time, approaching but never reaching. This creates a paradox. From your perspective, you cross the event horizon in finite time, maybe a few seconds for a stellar mass black hole, maybe hours for a supermassive one. Nothing special happens. You keep falling. But from an outside perspective, you never cross. You're frozen at the horizon forever. Both perspectives are correct. Both are equally valid descriptions of reality. The universe contradicts itself. And this isn't a problem with our theories, this is what general relativity predicts. Reality actually behaves this way. Now let's talk about rotating black holes because they're even stranger. Most black holes rotate. They formed from rotating stars, and conservation of angular momentum means they spin rapidly. A rotating black hole is called a Kerr black hole, and the geometry around it is profoundly weird. A non-rotating black hole has a spherical event horizon. A rotating black hole has an oblate event horizon flattened at the poles, bulging at the equator. And outside the event horizon, there's another boundary, the ergosphere. Inside the ergosphere, space itself is dragged along with the black hole's rotation. This is called frame dragging, and it means you can't stay still. You're forced to orbit the black hole, dragged along by space-time itself. You can still escape from the ergosphere. You just can't remain stationary relative to distant stars. But the really weird part is the singularity. In a non-rotating black hole, the singularity is a point all the mass crushed to infinite density at the center. But in a rotating black hole, the singularity is a ring, a circle of infinite density, rotating at the black hole's equator. And here's the disturbing part. The ring singularity has a hole in the middle. Mathematically, you could pass through the ring without hitting the singularity. And according to the equations, if you did that, you wouldn't die. You'd emerge somewhere else, either in a different region of space-time, a wormhole, or possibly in a different time. Rotating black holes might be time machines. The math is solid. The Kerr metric, the equations describing rotating black holes, contains closed time-like curves. These are paths through space-time that loop back on themselves, allowing you to arrive at an earlier time than you departed. Travel through the ring singularity the right way, and you could emerge in the past. Before you get excited, no, we can't use this for time travel. First, you'd have to survive falling into a black hole, which is essentially impossible. Second, the interior geometry of real black holes probably isn't stable. Quantum effects likely destroy the ring singularity before you reach it. Third, closed time-like curves create causality paradoxes that might be physically impossible. But the fact that our best theory of gravity predicts time machines inside rotating black holes is deeply unsettling. It means either general relativity is wrong, or the universe allows time travel under certain conditions, or something prevents closed time-like curves from forming. We don't know which. Now let's talk about Hawking radiation, because this is where black holes get truly paradoxical. In the 1970s, Stephen Hawking discovered that black holes aren't actually black. They emit radiation. Not much a stellar mass black hole has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background, but they emit. Here's why. Quantum mechanics says vacuum isn't empty, it's filled with virtual particles, particle-antiparticle pairs that spontaneously appear and annihilate. Normally, these pairs exist for such a short time that they can't be detected. But near a black hole's event horizon, something strange happens. A particle-antiparticle pair appears right at the horizon. One particle falls into the black hole, the other escapes. To an outside observer, it looks like the black hole emitted a particle. This is Hawking radiation, and it causes the black hole to lose mass. Very slowly, a solar mass black hole would take 1,067 years to evaporate completely, longer than the current age of the universe, but it happens. Black holes aren't eternal. They evaporate, eventually disappearing in a final burst of radiation. This creates a devastating paradox. Black holes destroy information. Here's the problem. Information in physics is conserved. The quantum state of a system is never lost. If you burn a book, the information isn't destroyed. It's just scrambled into smoke and ash. In principle, if you knew the exact quantum state of every particle in the smoke, you could reconstruct the book. But black holes seem to violate this. Information falls into a black hole, crosses the event horizon, and is lost forever. Then the black hole evaporates via Hawking radiation, which is thermal random, containing no information about what fell in. The information is gone, destroyed. This is the black hole information paradox, and it's one of the biggest unsolved problems in physics. If information is destroyed, quantum mechanics is wrong. If information isn't destroyed, general relativity is wrong. One of our most fundamental theories has to be incorrect. Some physicists think information is encoded in the Hawking radiation in subtle ways we don't understand. Others think information is stored at the event horizon in a holographic structure. Others think information really is destroyed, and we need to revise quantum mechanics. We don't know. The paradox remains unsolved. Finally, let's talk about what's actually inside a black hole, because the honest answer is, we have no idea. General relativity predicts a singularity, a point of infinite density, where space-time curvature becomes infinite, where the equations break down and produce nonsense. At the singularity, density is infinite, tidal forces are infinite, space-time is infinitely warped. But infinite in physics usually means the theory doesn't apply anymore. We don't actually think. There's a point of infinite density. We think quantum gravity, a theory we don't have yet, takes over before that, doing something that prevents the singularity from forming. Some theories suggest the singularity is replaced by a Planck scale structure, a tiny region where quantum effects dominate. Others suggest a singularity bounces, creating a new universe on the other side, a white hole. Others suggest black holes are fuzzballs, tangled masses of strings with no interior at all. The truth is, we don't know. General relativity says there's a singularity, but general relativity breaks down there, so we can't trust the prediction. Quantum mechanics should tell us what happens, but we don't have a quantum theory of gravity. The interior of a black hole is literally beyond our current understanding of physics. What we do know is this: black holes are places where our theories fail. They're not just objects, they're laboratories for discovering where physics is incomplete. They're proof that we don't understand the universe as well as we'd like, and they're utterly, profoundly, nightmarishly strange. Not just heavy objects with strong gravity, but regions where space-time breaks, where causality becomes ambiguous, where time and space swap roles, where information might be destroyed and reality contradicts itself. Black holes are the universe showing us that it's stranger than we can imagine, stranger than our best theories can describe, stranger than might be possible. And somewhere in the Milky Way, right now, matter is crossing an event horizon, falling into a place where the laws of physics stop making sense, where time stops and space tears and reality ends. Now we need to talk about quantum mechanics. And I'm warning you right now, this section is going to make you uncomfortable. Not because it's complicated, the basic concepts are actually quite simple, but because the implications are so profoundly weird, so fundamentally opposed to common sense, that even physicists who work with quantum mechanics every day aren't sure what it means. Here's the problem. According to quantum mechanics, particles don't have definite properties until you measure them. Before measurement, they exist in what's called a superposition, a ghostly combination of all possible states. Only when you look does reality choose which state to show you. And here's the disturbing part. This isn't a measurement problem or an issue with our instruments. This is how reality actually works. The universe literally doesn't decide what's real until something observes it. Let me show you why this is so unsettling. The double-slit experiment is the most famous demonstration in quantum mechanics, and it's been called the central mystery of the field. It's simple enough to do in a high school lab, yet it reveals something so strange about reality that we still don't have a satisfying explanation for it. Here's the setup. You have a light source, a barrier with two slits, and a screen behind it. Fire photons, particles of light at the slits one at a time. Each photon goes through one slit or the other and hits the screen. Logically, you'd expect two bright bands on the screen one behind each slit, where photons that went through that slit accumulated. That's what you'd see if you fired bullets through two holes in a wall, but that's not what happens. Instead, you see an interference pattern, multiple bright and dark bands, the kind of pattern you get when waves overlap and either reinforce or cancel each other out. The photons are behaving like waves, somehow going through both slits simultaneously and interfering with themselves. Okay, strange, but maybe photons are waves. Light is electromagnetic radiation, after all. Waves make interference patterns. Mystery solved, right? Wrong, because here's where it gets disturbing. Set up detectors at the slits to see which slit each photon goes through. Now fire photons one at a time again. Each detector clicks when a photon passes through its slit. You can verify that each photon goes through exactly one slit. Never both, never neither. Single particles going through single slits. And the interference pattern disappears completely. Now you see two bands, exactly what you'd expect from particles. The act of measuring which slit the photon went through changed the outcome. The photon behaves like a wave when you're not watching, somehow going through both slits, interfering with itself, creating the pattern. But it behaves like a particle when you're watching, going through exactly one slit, no interference. And this isn't an artifact of clumsy detectors disturbing the photons. You can make the measurement arbitrarily gentle, Use techniques that don't physically interact with the photons. Doesn't matter. The pattern disappears the moment you gain information about which slit was used. It's not the physical act of measurement that matters. It's the information. If you know which path the photon took, even if you haven't looked at the data yet, even if you never look, the interference vanishes. The universe responds to what could be known, not what is known. But wait, it gets worse. The delayed choice quantum eraser experiment, performed in the 1990s, takes this weirdness to another level. In this version, you don't decide whether to measure which slit the photon went through until after the photon has already hit the screen. Let that sink in. The photon hits the screen. That event is over, done, recorded. Then, after the fact, you choose whether to measure which path information. And depending on your choice made after the photon arrived, the photon either does or doesn't show interference. Your future choice retroactively determines whether the photon behaved like a wave or a particle in the past. Causality runs backward. The future affects the past. Some interpretations try to avoid this by saying the choice doesn't actually affect the past. It just affects which subset of outcomes you see. But that's semantic gymnastics. The experimental results are clear. Your choice about whether to measure, made after the quantum event occurred, determines what kind of event it was. This is not a fringe result. This is mainstream quantum mechanics, confirmed by dozens of experiments. Reality doesn't become definite until you look at it. And apparently, when you look, doesn't have to be after the event chronologically. It can be causally after, which might be chronologically before. So what does this mean? What's actually happening? The Copenhagen interpretation, the standard textbook explanation, says that particles exist in superposition until measured. Before measurement, the photon doesn't go through the left slit or the right slit. It goes through both in a superposition state. The wave function describes this superposition mathematically, encoding all possible outcomes. When you measure, the wave function collapses. Instantly, the superposition vanishes, and reality picks one outcome. The photon was in both places. Now it's in one place. The transition is discontinuous, instantaneous, and non-deterministic. You can't predict which outcome will occur, only the probabilities. But this raises an obvious question. What counts as a measurement? What causes collapse? And this is where things get existentially disturbing, because no one knows. Quantum mechanics doesn't define measurement. The theory works perfectly for calculating probabilities, but it doesn't say what actually happens during measurement, what counts as an observer, or why superposition ends. Some physicists think consciousness is required. The wave function collapses when a conscious observer becomes aware of the measurement result. Before that, everything remains in superposition. This is the von Neumann-Wigner interpretation, and yes, it seriously suggests that consciousness plays a fundamental role in physics. Think about the implications. If consciousness causes collapse, then the universe was in a superposition until the first conscious observer appeared. All of cosmic history, the formation of galaxies, stars, planets, existed in ghostly superposition, not actually real, until some organism evolved consciousness and looked. And it's still happening. Right now, quantum systems throughout the universe are in superposition. They don't have definite properties. The atoms in the walls around you, the photons streaming from the sun, distant galaxies, all in superposition, not fully real, until something conscious observes them. You're not just observing the universe, you're creating it. Your consciousness is collapsing wave functions, forcing reality to become definite. Without observers, maybe nothing is real. Other interpretations avoid this conclusion. The many worlds interpretation says wave functions never collapse, all outcomes happen in different branches of reality. When you measure the photon's position, the universe splits. In one branch, you see the photon at position A. In another branch, you see it at position B. Both outcomes are real, just in different worlds. This sounds like science fiction, but it's a legitimate interpretation taken seriously by many physicists. It solves the measurement problem elegantly. There is no collapse, no special role for observers, just the deterministic evolution of the wave function. The price is accepting that reality is constantly branching, that every quantum event creates new universes, that there are infinitely many versions of you experiencing different outcomes. The pilot wave interpretation says particles always have definite positions, guided by a pilot wave that determines their motion. Superposition is real. The pilot wave goes through both slits, but the particle goes through only one, guided by the wave's interference pattern. No collapse, no observer effect, no consciousness required. But this interpretation has its own weirdness. The pilot wave is non-local. It instantaneously responds to changes anywhere in space. And it exists in configuration space, a high-dimensional mathematical space encoding all particle positions, not in regular three-dimensional space. It's ontologically bizarre. Other interpretations, relational quantum mechanics, consistent histories, objective collapse theories, all have their own strange implications. None of them restore the common-sense world where objects have definite properties independent of observation. Here's the thing. We don't know which interpretation is correct. They make the same experimental predictions, so we can't distinguish them empirically. This isn't a failure of current technology. It's unclear if any experiment could ever distinguish them. We might be stuck with permanent ambiguity about what quantum mechanics means. But one thing is certain. Reality at the quantum level is nothing like reality at the human scale. Particles genuinely don't have definite properties until measured. Superposition is real. The observer effect is real. And somehow observation, whatever that means, transforms ghostly probabilities into actual outcomes. Let me give you another example. Schrödinger's cat. You've heard of this probably as a joke about a cat that's both alive and dead. But it's not a joke, it's a serious problem. Put a cat in a sealed box with a device that has a 50% chance of releasing poison within an hour, triggered by a quantum event, say, a radioactive atom decaying. Close the box. Wait an hour. Before you open the box, according to quantum mechanics, the system is in superposition. The atom has both decayed and not decayed. The poison is both released and not released. The cat is both alive and dead. This is absurd. Cats aren't in superposition. They're definitively alive or dead, regardless of whether anyone's looking. But quantum mechanics says the superposition persists until you open the box and observe the result. Schrödinger proposed this thought experiment to show that quantum mechanics leads to ridiculous conclusions when applied to macroscopic objects. He thought it was a reductio ad absurdum proof that the Copenhagen interpretation was wrong. But experiments have confirmed quantum superposition for increasingly large objects. molecules with hundreds of atoms, tiny mechanical oscillators. Recent experiments have shown quantum effects in objects visible to the naked eye. The boundary between quantum and classical is blurry, not sharp. So maybe macroscopic superposition is real. Maybe cats can be in superposition, or would be if we could isolate them from environmental interactions. Maybe the only reason we don't see quantum weirdness at large scales is decoherence, the environment constantly measuring the system, collapsing the wave function so quickly that superposition never lasts. Which brings us to the most disturbing implication of all. If consciousness causes collapse, if observation is what makes reality definite, then what happens to unobserved parts of the universe? The Andromeda Galaxy is 2.5 million light-years away. Photons from it have been traveling for 2.5 million years to reach us. Before they arrive, before any conscious observer sees them, is Andromeda real? Or is it in superposition, not fully actual, waiting for observation to make it definite? What about regions of space no one has observed yet? The far side of the moon before spacecraft photographed it, was it real? The deep ocean floor before submarines explored it, was it definite? Or did these places exist in quantum superposition until consciousness observed them? And here's the ultimate question. Was the entire universe in superposition until the first conscious observer evolved? Did billions of years of cosmic history exist only as ghostly probabilities not becoming real until something could think? Some physicists take this seriously. The participatory anthropic principle, proposed by John Wheeler, suggests that observers are necessary to bring the universe into existence. Not that observers created the universe, that's backwards, but that the universe and observers co-create each other. The universe evolves conditions suitable for consciousness, and consciousness, through observation, makes the universe real. It's a strange loop. The universe creates observers, and observers create the universe. Both statements are true simultaneously. Reality bootstraps itself into existence through this self-referential process. This sounds mystical, but it might be true. We don't know. That's the honest answer. Quantum mechanics works perfectly as a calculational tool, but we don't understand what it means. And until we do, we're left with the unsettling possibility that the universe doesn't exist, at least not in a definite way until something observes it. That consciousness might be fundamental to reality, not an emergent byproduct of complex matter, but a necessary ingredient for existence itself. You might not just be in the universe. The universe might need you to be real. Your observation right now, watching this video, is collapsing wave functions, forcing probability into actuality, creating definite reality from quantum possibilities. Without you, without conscious observers like you, maybe nothing would be real. Maybe the universe would be an undifferentiated probability wave, all possible states superimposed, nothing definite, nothing actual. So next time you look at something, anything, remember, you're not just passively observing, you might be creating. Your consciousness might be the boundary between the possible and the actual, between quantum ghosts and classical reality, between nothing and something. The universe might literally not exist without you watching it, and we have no idea why. Look up at the night sky. Stars scattered across the darkness, the moon hanging bright and familiar, maybe a planet or two visible near the horizon. It's beautiful, peaceful. Ancient peoples looked at the same sky, saw the same constellations, felt the same sense of wonder. But here's the thing, none of what you're seeing is real. Not in the sense of happening now. Everything you see in the sky is a lie, a historical record, a ghost, light from events that already ended. You're not looking at the present, you're looking at the past, sometimes the distant past. Let me explain why everything you see in the universe is already gone. Light travels at 299,792 kilometers per second. That's fast nothing, and the universe moves faster. But the universe is big, really big. So big that even at light speed, traveling between objects takes time. Sometimes a lot of time. The sun is about 150 million kilometers away. Light from the sun takes approximately 8 minutes and 20 seconds to reach Earth. This means when you look at the sun, please don't actually look at the sun. You're seeing where it was 8 minutes ago. The sun you perceive is the sun of the past. Right now, the actual sun, the sun that exists in the present moment, is in a slightly different position than you see it. Earth has moved along its orbit. The sun has moved relative to the galactic center. Everything has shifted, but you don't see any of that. You see the old sun, the historical sun, the sun that existed 8 minutes ago. And here's the disturbing implication. The sun could have exploded 7 minutes ago, and you wouldn't know. You'd sit here, comfortable and alive, watching a sun that no longer exists for one more minute. Then the last photons would arrive, followed immediately by the expanding shock wave of plasma, and Earth would be incinerated before anyone even knew something was wrong. This isn't theoretical. This is reality. There's an 8-minute delay in all information from the sun. Not just light everything. Gravitational waves, neutrinos, well, neutrinos travel at nearly light speed. Any signal. The speed of light is a hard limit on information transfer, and it means you can never know what's happening at the sun right now. Only what happened 8 minutes ago. The moon is closer about 1.3 light seconds away. When you look at the moon, you're seeing where it was 1.3 seconds ago. This becomes important for lunar missions. When NASA communicates with astronauts on the moon, there's a 2.6-second delay, round trip 1.3 seconds for the signal to reach the moon, 1.3 seconds for the response to come back. Conversations require patience, but 1.3 seconds is nothing compared to the planets. Mars, at its closest approach to Earth, is about 4 light minutes away. When Mars rovers send images back to Earth, those images are at minimum 4 minutes old by the time we see them. Commands sent to the rovers take 4 minutes to arrive. This makes real-time control impossible. Rovers must be autonomous, capable of making decisions without waiting for instructions from Earth. When Mars is on the opposite side of the Sun from Earth, the distance increases to about 24 light minutes. Same object, but now the delay is 6 times longer, just because of orbital mechanics. The Mars you see at closest approach is 4 minutes old. The Mars you see at farthest distance is 24 minutes old. Same planet, different delays. Jupiter is worse. At closest approach, about 33 light minutes away. At farthest, about 52 light minutes. Almost an hour into the past. When the Juno spacecraft orbits Jupiter, scientists on Earth see data that's 40 minutes old on average. The Jupiter they observe is historical, significantly outdated by human timescales. Neptune is even more extreme, about 4 light hours away. The stunning images from Voyager 2 when it flew past Neptune in 1989, those images were 4 hours old when received on Earth. The spacecraft was taking pictures of a Neptune that existed 4 hours earlier, and scientists on Earth saw those pictures 4 hours after they were taken. An 8-hour delay between the actual event and human observation. But these are solar system objects, our local neighborhood. The real nightmare begins when we look at stars. The nearest star to the Sun is Proxima Centauri, about 4.24 light years away. Every photon of light from Proxima Centauri takes 4.24 years to reach us. When you look at Proxima Centauri, you can't actually. It's too dim for naked eye observation, but if you could, you'd see the star as it was 4.24 years ago. Proxima Centauri could have exploded in 2023, and we won't know until 2027. It could have been destroyed by an alien civilization. It could have been ejected from its orbit by a passing black hole. Anything could have happened, and we're blind to it, seeing only the ancient light from a star that might not exist anymore. Now look at the visible stars in the night sky. Sirius, the brightest star, is 8.6 light years away. The Sirius you see is 8.6 years old. Vega is 25 light years away. Betelgeuse is about 650 light years away. When you look at Betelgeuse, that red supergiant in Orion's shoulder, you're seeing light that left the star in the 1370s, medieval times, the 100 Years' War, long before Columbus. That's how old the light is, and Betelgeuse is probably going to explode. It's a supernova candidate, a massive star nearing the end of its life. It could explode any time in the next million years, which in cosmic terms means it could explode tonight. Or it could have already exploded centuries ago, and we won't know until the light reaches us. Imagine, one night you go outside and see a new star brighter than Venus, visible even during the day. Betelgeuse has exploded, releasing as much energy in a few weeks as the Sun will in its entire 10 billion year lifetime. The supernova is spectacular, studied by astronomers worldwide, visible to the naked eye for months, but it didn't happen when you saw it. It happened 650 years ago. The star actually exploded in the 1370s, and the light just now reached us. The event is ancient history, and we're only seeing it now because light is slow and space is big. This is true for every star you see. The night sky is a time machine, showing you the universe at many different moments in history simultaneously. That star is 10 years old. That one is 100 years old. That one is 1,000 years old. You're seeing them all now, but they're all from different thens, and some of them are already dead. Statistically, several of the visible stars in the night sky have already exploded or died. We're looking at corpses, ghosts, light from objects that no longer exist. The star might be gone, collapsed into a white dwarf or neutron star or black hole, but its light is still traveling, still reaching us, still showing us a star that isn't there anymore. You are quite literally looking at the past every time you look up. But wait, it gets worse, much worse, because we haven't even left the galaxy yet. The Andromeda Galaxy is 2.5 million light years away. Every photon you see from Andromeda left that galaxy 2.5 million years ago. When you look at Andromeda, it's visible to the naked eye on dark nights. You're seeing what it looked like when Homo habilis was using stone tools in Africa, before Homo erectus. before humans existed in any form you'd recognize. The Andromeda you see is 2.5 million years old. Anything could have happened there in the intervening time. A supernova could have sterilized the galaxy. An alien civilization could have risen, colonized every star, and fallen. A gamma-ray burst could have scoured one entire spiral arm. We wouldn't know. We're seeing ancient history. And here's the really disturbing part. Andromeda is on a collision course with the Milky Way. The two galaxies are approaching each other at about 110 kilometers per second. In about 4.5 billion years, they'll collide, merging into a single elliptical galaxy astronomers have nicknamed Milkomeda. But we're seeing Andromeda as it was 2.5 million years ago. The Andromeda that exists right now, the one simultaneous with this moment, is 2.5 million years of travel closer than what we see. We're seeing where Andromeda was, not where it is. Could the collision have already started? No, the math doesn't work out. We have billions of years. But the point stands, we don't see Andromeda as it exists now. We see a historical Andromeda, and the galaxy's current state is hidden from us by the speed of light. The farther you look, the worse it gets. The most distant galaxies visible to Hubble are about 13.4 billion light years away. Those galaxies, small, irregular, primitive, are shown as they were 13.4 billion years ago, just a few hundred million years after the Big Bang. Those galaxies don't look like that anymore. They've had 13.4 billion years to evolve. They've probably merged with other galaxies, formed spiral structures, produced trillions of stars, some of which lived and died. The galaxies we see in deep field images are baby pictures. The actual galaxies as they exist right now are mature, evolved, completely different, and we'll never see them as they are now. The light showing their current state won't reach us for another 13.4 billion years. By then, the sun will be long dead, Earth will be gone, and no one will be here to observe. This creates something called the past light cone. Every point in space-time has a light cone, the region of space-time it can causally interact with. Your past light cone is the set of all events whose light has had time to reach you. Everything you've ever seen, everything you could possibly see right now, is inside your past light cone. And here's the key. Your past light cone is finite. There are events in the universe, distant events, recent events that are outside your light cone. Their light hasn't reached you yet. You cannot see them. You cannot know about them. They're beyond your cosmic horizon. This means there are parts of the universe you will never see, even in principle. The expansion of space means distant galaxies are receding faster than light can close the gap. Their light will never reach us. They're beyond our observable universe, permanently hidden, invisible not because of limitations in our telescopes, but because of the structure of space-time itself. Right now, somewhere beyond the cosmic horizon, galaxies exist that we will never observe. Stars are being born. Planets are forming. Maybe life is evolving, and we'll never know. The information can't reach us. Those regions of space are, for us, non-existent, not because they aren't real, but because they're causally disconnected from us. Everything you see is in the past. The farther away something is, the older the light. Looking out in space is looking back in time. The observable universe isn't a snapshot of how things are now. It's a layered image showing different moments in cosmic history, all superimposed. When you look at the moon, you see 1.3 seconds into the past. The sun, 8 minutes. Nearby stars, years or decades. Distant stars, centuries or millennia. Galaxies, millions or billions of years. The cosmic microwave background, the most distant thing we can see, shows the universe as it was 13.8 billion years ago, just 380,000 years after the Big Bang. You're not seeing the universe as it is. You're seeing the universe as it was at many different times, all mixed together. The present, the universal now, containing all events happening simultaneously, is hidden from you, veiled by the finite speed of light, inaccessible except for the immediate vicinity. And even your immediate vicinity isn't really now, it's nanoseconds ago. Light from objects across the room takes nanoseconds to reach your eyes. Your brain takes milliseconds to process the signal. By the time you're consciously aware of seeing something, it's already in the past 10 to 80 milliseconds ago, depending on the neural processing required. You never see the present, ever. You live in the past, perceiving events that already happened, making decisions based on outdated information, forever chasing a now that retreats faster than you can catch it. The sun you see is gone. The stars are fossils. The galaxies are ancient history. And the present, the real, actual present, is invisible, hidden, unknowable, except through extrapolation and inference. You're not looking at the universe. You're looking at the universe's past. And the farther you look, the deeper into history you see, until you're looking at the edge of time itself, at the moment when light first traveled freely through space, carrying information from the universe's infancy. Everything you see is already gone. The present is invisible, and the speed of light ensures you'll never catch up. Welcome to reality, where the past is all you get, and the present is forever out of reach. Let's talk about the ways the universe is actively trying to kill you. Not metaphorically, not eventually, but literally, right now, through physical processes that could erase you and everything else without warning. You're living on borrowed time in a universe that's fundamentally unstable, where existence itself might be temporary. And the worst part? Some of these threats could already be underway. You could be seconds away from annihilation, and you'd never know until the moment reality ended. Let's start with the most terrifying: false vacuum decay. The universe might be metastable. That's a physics term meaning stable for now, but not permanently. Like a ball balanced on a hilltop, it's stationary, but the slightest push will send it rolling down to a lower energy state. Our universe might be that ball. Here's how it works. Quantum fields permeate all of space. These fields have energy states, different configurations they can exist in. The lowest energy state is called the true vacuum. Any higher energy state is called a false vacuum. If the universe is in a false vacuum state, it's like being in a valley on a hillside. You're stable for now. There's a barrier preventing you from rolling further down. But somewhere lower, there's a deeper valley, the true vacuum. And if the universe ever transitions from false vacuum to true vacuum, everything changes, instantly, catastrophically. This transition would happen through quantum tunneling. Somewhere in space, randomly, a bubble of true vacuum would spontaneously appear. Inside that bubble, the laws of physics would be different. Particle masses would change. The strength of fundamental forces would shift. Atoms as we know them couldn't exist, and that bubble would expand at the speed of light. Nothing inside the bubble survives. Matter disintegrates. Energy levels shift. Everything that depends on the current vacuum state, which is everything ceases to exist. Not destroyed exactly, but transformed into something so radically different that nothing recognizable remains. You wouldn't see it coming. The bubble expands at light speed, which means the light warning you of its approach arrives at the exact same moment as the bubble itself. One instant you exist. The next instant, the expanding wall of true vacuum reaches you and you're gone. No transition, no warning, just sudden, absolute annihilation. And here's the truly horrifying part. This could be happening right now. A bubble of true vacuum could have nucleated 1 billion light years away, 1 million years ago. It's expanding toward us at light speed. The wave of destruction has been traveling through space for 1 million years, erasing galaxies, sterilizing cosmic voids, racing toward the Milky Way, and we wouldn't know, couldn't know. The information can't reach us faster than the bubble itself. We're blind to our own doom, sitting here comfortable and ignorant, while an expanding sphere of annihilation approaches at 300,000 kilometers per second. Could this happen? Is the universe actually metastable? We don't know. Current measurements of the Higgs boson mass and top quark mass suggest our vacuum might be metastable. The numbers are right on the edge close enough that experimental uncertainties matter. Some calculations say we're stable. Some say we're metastable. Some say we're unstable and should have decayed already. The fact that we exist suggests either we're in a stable vacuum or we're in a metastable vacuum with an extremely long half-life. The vacuum could last YHA years before decaying far longer than the current age of the universe. Or it could decay tomorrow. The probability is low but non-zero. And if it happens, it happens. Nothing can stop it. No technology, no warning system, no escape. The bubble expands at light speed. You can't outrun it. You can't see it coming. You can't prevent it. You just stop existing. Sleep well tonight, knowing that false vacuum decay is physically possible, might be inevitable, and could erase the observable universe at any moment without warning. But false vacuum decay is just one existential threat. Let's talk about the certain doom: heat death. The second law of thermodynamics states that entropy disorder always increases in a closed system. The universe is a closed system. Therefore, entropy is always increasing. Energy is spreading out, becoming less concentrated, less useful. And this process is irreversible. Eventually, far in the future, but inevitably the universe will reach maximum entropy. All energy will be evenly distributed. Temperature will be uniform everywhere. No gradients will exist to drive processes. Stars will burn out. Black holes will evaporate. Even protons will decay, leaving nothing but a thin soup of photons and leptons in an ever-expanding void. And this is heat death, the point at which the universe reaches thermodynamic equilibrium. Nothing can happen anymore because there's no available energy to make things happen. No stars shine, no planets orbit, no chemistry occurs. No life exists, can't exist, because life requires energy gradients, requires order maintained against entropy, and there's no order left. Just infinite darkness, infinite cold, infinite stillness. Forever. This isn't speculation. This is what thermodynamics predicts. The timeline is long, 10,100 years or more, but it's inevitable. The universe will die. Not in a dramatic explosion, not in a sudden catastrophe, but in a slow, cold fade-out into nothingness. and nothing can prevent it. You can't fight entropy. It's not a force or an entity, it's a statistical inevitability, a consequence of probability itself. Systems tend toward disorder because there are vastly more disordered states than ordered ones. Order is rare, disorder is common, and over time everything drifts toward what's common. Stars will burn out. The last red dwarfs, the longest-lived stars, which can burn for trillions of years, will eventually exhaust their fuel. No new stars will form because all the gas will be locked in stellar remnants or dispersed too thinly to collapse. The universe will go dark. Black holes will dominate for a while, but even they aren't eternal. Hawking radiation causes black holes to evaporate slowly over timescales that dwarf the current age of the universe. A solar mass black hole takes 1,067 years to evaporate. Supermassive black holes take 10,100 years, but eventually even they disappear. The last black hole evaporates, releasing its final burst of radiation into the void, and then there's nothing left, just photons and neutrinos, and maybe some exotic particles all spread so thinly that they might as well not exist. If protons decay, and some theories predict they do, with a half-life around 1,034 years, then even matter itself is temporary. Wait long enough and all protons decay into lighter particles, leaving no atoms, no chemistry, no possibility of structure. The universe becomes a cold, dark, empty void, expanding forever, cooling forever, approaching absolute zero, but never quite reaching it. Nothing happens, nothing can happen. The concept of event becomes meaningless because there's no change, no process, no energy to drive anything. This is the guaranteed future, not a possibility, a certainty. The universe has an expiration date, written into the laws of thermodynamics. We're living in the brief, anomalous period when the universe is young and hot and interesting, but that's temporary. The long-term state is heat death. Entropy always wins, always. But maybe heat death isn't the actual end. Maybe something worse happens first, the Big Rip. This depends on dark energy, the mysterious force causing the universe's expansion to accelerate. Dark energy pushes space apart, making galaxies recede faster and faster. The farther apart they are, the faster they recede, which is why the expansion accelerates. Current observations suggest dark energy is constant, a cosmological constant, same everywhere, unchanging over time. But what if it's not? What if dark energy gets stronger? If dark energy density increases over time, a scenario called phantom energy, the expansion accelerates faster and faster without limit. Eventually, the acceleration becomes so extreme that it tears everything apart. First, galaxy clusters unbind. The expansion overwhelms gravity, and galaxies drift apart, unable to hold together gravitationally. This happens billions of years from now. Then individual galaxies unbind. Stars are ripped away from each other, scattered into the void. The Milky Way comes apart, stars flying off in all directions. This happens closer to the Big Rip, maybe tens of millions of years before. Then, solar systems unbind. Planets are torn from their orbits, flung into interstellar space. Earth separates from the Sun. This happens months before the Big Rip. Then, planets themselves are torn apart. The expansion becomes so extreme that it overwhelms the electromagnetic forces holding matter together. Earth disintegrates into fragments, then into atoms. This happens minutes before the Big Rip. Then atoms are torn apart. Electrons are ripped from nuclei. Nuclei themselves disintegrate. Matter ceases to exist. This happens fractions of a second before the Big Rip. Finally, space-time itself tears. The expansion becomes infinite. The universe rips apart at the most fundamental level, destroying not just matter and energy, but the very fabric of space and time. And then, what? No one knows. The Big Rip is literally the end of physics. Beyond that point, our theories don't apply. Maybe a new universe forms. Maybe nothing exists. Maybe the question becomes meaningless. The good news? This probably won't happen. Current observations suggest dark energy is constant, not increasing. The universe will probably die of heat death, not the Big Rip. The bad news? We're not certain. Dark energy is mysterious. We don't know what it is or how it behaves. If it strengthens even slightly, the Big Rip becomes possible. And unlike heat death, which happens in the unimaginably distant future, the Big Rip could happen relatively soon, tens of billions of years, not 10,100 years. But let's return to immediate threats. False vacuum decay and cosmic rays from supernova aren't the only dangers. There's also gamma-ray bursts. Gamma-ray bursts are the brightest events in the universe's short-lived explosions that release more energy in seconds than the sun will in its entire lifetime. They're caused by collapsing massive stars or colliding neutron stars, and they beam radiation in tight jets. If a gamma-ray burst went off within a few thousand light-years of Earth, aimed directly at us, it could be catastrophic. The radiation would strip away Earth's ozone layer, causing mass extinction through ultraviolet exposure. It might have happened before the Ordovician extinction. 450 million years ago might have been caused by a nearby gamma-ray burst, and we wouldn't see it coming. If the burst is aimed at us, the gamma rays travel at light speed. The light warning us arrives at the same moment as the radiation itself. One instant, everything is fine. The next, Earth's atmosphere is bombarded with hard radiation. Could this happen soon? Probably not. Gamma-ray bursts require specific conditions, collapsing massive stars, precisely aimed jets, close enough proximity. The odds are low, but non-zero. There are stars within range that could produce gamma-ray bursts. Betelgeuse, for instance, though it's far enough that even a direct hit might not be catastrophic. Still, it's another way the universe could kill you without warning. Another existential threat lurking in the darkness, waiting for random chance to align. So let's summarize. The universe is unstable. Our vacuum might be metastable, ready to decay into a lower energy state that destroys everything. The expansion might accelerate into a Big Rip, tearing matter apart at the atomic level. Gamma-ray bursts could sterilize Earth without warning. And even if we avoid all that, entropy guarantees eventual heat death, a slow, cold fade-out into eternal nothingness. You're living in a universe that's trying to kill you. Not actively, the universe doesn't care about you, but passively, through physical processes that make existence temporary and precarious. You're alive now only because none of the disasters have happened yet. Give it time. The universe is patient, and entropy always wins. But here's the real nightmare. Some of these processes might already be underway. False vacuum decay could have started 1 billion years ago, and the expanding bubble is racing toward us. We don't know, can't know, won't know until the moment it arrives. You could be living in the last generation before everything ends, or the universe could persist for 10,100 years. Both are possible. Both are consistent with current physics, and you'll never know which until it's too late. So enjoy existence while it lasts, because the universe will definitely kill you. Maybe soon, maybe later, but definitely, inevitably, without exception. Your atoms will disperse, your pattern will dissolve, and eventually, long after you're gone, the universe itself will fade into darkness, cold and empty and eternal. Nothing escapes entropy, nothing escapes heat death, and maybe, just maybe, nothing escapes false vacuum decay either. Here's the most disturbing idea in modern philosophy. You're probably not real. Not in the way you think you are. You might be a simulation, a pattern of information running on a computer in some higher reality, experiencing a universe that doesn't actually exist except as computation. This isn't science fiction. It's a serious philosophical argument that physicists and philosophers take seriously. And the more you think about it, the harder it becomes to dismiss. The simulation hypothesis goes like this. If it's possible to create realistic simulations of conscious beings, then statistically you're almost certainly in one. Here's why. Imagine a civilization advances to the point where it can run detailed simulations of universes, complete with conscious inhabitants who don't know they're simulated. Call this a posthuman civilization, one with technology far beyond ours. If posthuman civilizations exist, they could run millions or billions of simulations. Each simulation contains billions of conscious beings. Meanwhile, there's only one base reality, the original unsimulated universe. So we have one base reality with, say, 10 billion people, and a million simulations, each containing 10 billion people. That's 10 trillion simulated people versus 10 billion real people. The ratio is 1,000,000 to 1. If you're a randomly selected conscious being from this multiverse of real and simulated worlds, what are the odds you're in base reality? 1 in 1,000,000. Statistically, you're almost certainly simulated. The only way to avoid this conclusion is to argue that posthuman civilizations never create simulations. Either they can't, simulation is impossible, or they won't, they choose not to, for ethical reasons or lack of interest. But why would simulation be impossible? We're already building crude simulations. Video games create simplified worlds with quasi-realistic physics. Whole brain emulation might be possible, eventually scanning a brain, modeling every neuron, running the simulation on hardware. If consciousness is computational, and most neuroscientists think it is, then simulating consciousness is just a matter of sufficient computing power. And why would posthuman civilizations not create simulations? Maybe they find it unethical, but it only takes one civilization, one group within that civilization, even one person, to run simulations. If it's technologically possible, someone will do it. And if they do, they'll probably run many simulations, not just one. So the math suggests you're probably simulated. But is there evidence? Consider the structure of reality. Quantum mechanics looks suspiciously like a computer program optimizing resource usage. The universe doesn't render unobserved details. Particles exist in superposition until measured, like a game engine not rendering parts of the map the player can't see. The speed of light looks like a frame rate limit. Planck length looks like pixel size. The universe has discrete units, not infinite resolution. This could be coincidence, or it could be evidence that reality is computational. Then there's the fine-tuning problem. The fundamental constants of physics, the strength of gravity, the mass of the electron, the cosmological constant are precisely calibrated to allow complex structures like atoms, stars, and life. Change any constant by even a tiny fraction, and the universe becomes sterile, no stars, no chemistry, no observers. This fine-tuning is baffling. Why are the constants exactly what they need to be for life? One explanation. We're in a simulation designed to produce observers. The simulators set the parameters to allow life because that's what they wanted to study. Could we detect the simulation? Maybe. If the simulation has limited resolution, we might find glitches, tiny errors, rounding mistakes, places where the code breaks down. Some physicists have proposed looking for these. So far, nothing definitive. But the absence of evidence isn't evidence of absence. A sufficiently advanced simulation would be indistinguishable from reality. The simulators could patch glitches in real time, edit memories, prevent detection. We'd never know. So here's the disturbing conclusion. You can't prove you're not in a simulation. And statistically, if simulations are possible, you're probably in one. Your entire life, every memory, every experience, every person you've met might be artificial. Patterns in some alien computer, as real as a video game character is real. Does it matter? If the simulation is perfect, indistinguishable from base reality, does the distinction mean anything? You experience consciousness, pain, joy, love. That's real, even if the substrate is computational. Or maybe it does matter. Maybe base reality has privileges simulations don't. Maybe simulations can be paused, edited, deleted. Maybe your existence is contingent on simulators maintaining interest. You're probably not real, and you can never know for sure. So where does all this leave us? You've learned that time doesn't flow the way you experience it, that you're made of dead stars, that black holes break physics, that consciousness might be fundamental to reality, that everything you see is ancient history, that the universe will definitely kill you, that you're probably simulated. These aren't fringe theories. These are consequences of our best physics, our most accurate descriptions of reality, and they're so strange, so fundamentally opposed to intuition, that most people never hear about them. But now you have, and you can't unknow it. The universe is stranger than we imagined, stranger than we can imagine. Every time we think we understand reality, we discover another layer of weirdness underneath. Time is relative, matter is energy, particles are waves, nothing is certain. Reality doesn't exist until observed. The past is as real as the present. Free will might be illusion. You might be code running on alien hardware. This should be disturbing. It should shatter your comfortable assumptions about existence. That's the point. Comfort is for people who haven't looked closely at what the universe actually is. But there's beauty in this too. Beauty in the strangeness, in the profoundness, in the sheer alien magnificence of reality operating according to rules that make no intuitive sense but work anyway. We're privileged to live in a time when we can understand these things, when we have telescopes and particle accelerators and mathematical frameworks to probe the nature of existence. You're a pattern of atoms forged in stars, organized by evolution into a form capable of understanding its own cosmic origins. Living temporarily in a universe that might be simulated will definitely end and doesn't make sense. And that's magnificent. Welcome to reality. It's weirder than you thought.